the material for what's actually on the final announcement. Okay, so the first section that I should say, what goes over for your homework is the concept of heat capacity. So a solid material, when heated, it experiences an increase in temperature, signifying that some energy has been absorbed, and that's essentially what heat capacity is. It indicates a material's ability to absorb heat from the external surroundings. So focus on this one. And it represents the amount of energy required to produce a unit of temperature rise. And mathematically, you can see it down there. So heat capacity is equal to energy input divided by temperature change. And I believe, yes, and then I mentioned units down there as well. And your book also mentions, is this the first one? No. And your book also mentions that there are two ways to measure heat capacity, which is the C subscript P there, Cp, which is just heat capacity at a constant pressure, and Cv, which is just heat capacity at a constant volume. And as noted here in the slide as well, the magnitude of Cp is always greater than or equal to the heat capacity at a constant volume. However, any difference is very slight for most solid materials at room temperature and below. So that was, I guess, the first concept. And you guys need to know. And they also discussed temperature dependence of the heat capacity. So the variation with temperature of the vibrational contribution to the heat capacity at constant volume for many relative simple crystalline solids can be shown here, like by this plot. And so the Cv is 0 at 0 Kelvin, but it'll rise rapidly with temperature. And this corresponds to an increased ability of the lattice waves to enhance their average energy with increasing temperature. And at low temperatures, the relationship between Cv and the absolute temperature of temperature T can be shown in this equation down here. So Cv is equal to A multiplied by Tq. This is just the dependence of heat capacity at a constant volume on temperature at a low temperature in units of Kelvin. I think that's pretty much it. Oh, and so on this plot they mentioned what you see there, the bi temperature. So above this temperatures, the Cv levels off and becomes essentially independent temperature at a value of approximately R, R being the gas constant. Okay, so that being said, I think this one is not too bad. I don't think too many people missed this one, but we'll go ahead and go over it. So this question is to what temperature would 25 pound meters of a 1025 steel specimen at room temperature be raised if 125 BTU of heat is supplied? I wish they would use metrics instead of English system, but it is what it is. So feel free to try that one, and I'll make sure I have it, understand it correctly in my head so I can help you guys go through it. Fortunately, it's not too involved. So for this problem, 19.2, they're asking us to determine the temperature at which the 25, what's it, pound meters? I think that's pound meter of steel emitted at 25 degrees Celsius or room temperature would raise if 125 BTU of heat is supplied. And so the first equation, which I don't believe was in this one was not there. So I write this equation and put it on the box for you guys. So this is accomplished by utilizing, this is basically a modified equation from your text, but this is the equation here. So as you change the temperature is equal to the change in the amount of heat supply divided by the mass, which is multiplied by Cp. And so from table 19.1 where you're supposed to get your heat constant or heat capacity at constant pressure, that value, at least for this material, you may have a different material. So for the 1025 steel, the heat capacity at constant pressure is 46 joules per kilogram Kelvin for steel. And since this is not in the US units, we gotta convert. And the conversion for that is essentially multiply this by 2.39 times 10 to the negative 4 BTU per pound meter Fahrenheit divided by 1 joule per kilogram Kelvin. And this will get you 0.116 BTU per Fahrenheit. So now that we have that converted, we can now figure out this temperature. So we have delta T is equal to 125 BTU multiplied by the pound at pound meter, and then multiply that by the Cp, which is 1.16. And that change in temperature is going to be 43.1 degrees Fahrenheit. And so to figure out the final temperature, because as we know, the change in temperature is just T naught plus or should be original minus final essentially. So we want the final temperature, which is equal to T naught plus delta T. I believe they mentioned I see. So this is 25 degrees Celsius, this would be 77 degrees Fahrenheit. So 77 degrees Fahrenheit added to the 43.1 degrees Fahrenheit that we have here. So this goes here. And the original temperature is just the 25 degrees Celsius, which is just 77 degrees Fahrenheit. You should end up with a final temperature of under 20.1 degrees Fahrenheit. So any questions on this one? No, not too bad. Just have to know the equation and then you start plugging things in. Unit conversion for SCP, pretty straightforward. Okay, so then quickly let's go ahead and run to the next question. So in number 19.3 here, they want us to determine the room temperature heat capacities at constant pressure for the following materials: aluminum, silver, tungsten, and 70% copper, 30% zinc, brass. And they want us to see how these two values compare with one another and basically explain it. So I remember this one. I'll show you guys basically how to run through the first one, but then the process is kind of the same for all the rest of the materials, so that way we won't spend too much time on that. So first this problem. So the problem is asking that we determine the room temperature heat capacities at the constant pressure CP for all these materials. And so essentially to solve for that, we just need to multiply the CP to table next to the test. Or I should say, table next to the values and multiply those values by the atomic weights of each of those materials. I think to account the conversion from grams to kilograms, if they have not been converted already. So, for example, for aluminum, the CP is that's multiplied by the conversion factor, 1 kilogram per 100 grams, multiplied by so now that we know how to essentially filling all this out, filling all that information with silver, we should end up with a CP of 5.4. And for the tungsten, we should have a CP of about to thermal recovery. So now for the brass, which I'll do over here, first, because we have an alloy here, we need to compute the atomic weight of the alloy. And to compute that, we have to use this equation here, which is the atomic weights of, I guess I write it as A subscript AB, so it's the atomic weight average of both of them. It's 100 divided by, this C should stand for the, yes, so the C is basically the composition of the copper divided by the atomic weight of the copper, and you add that to the composition of the zinc divided by the atomic weight of the zinc. And essentially, so we know the copper is 7% and the zinc is 38%. At this point, we just need the atomic weights for copper and zinc respectively. So I won't write those in just to save some space and time. So if we calculate that, we'll have the atomic weight of that alloy as 64.9 grams per mole. So now that we have that, now we can solve for the CP at room temperature for the brass, which again will do the same thing that we did before with the other ones, and it should end up with a CP of 24 points. Well, it's just 24, but it's not down here. So here is for the brass, and then the others. Silver and tungsten. Okay. So, any questions on this one? This one too, not that bad, but. So now quickly into this next question. So the problem reads for aluminum, the heat capacity at constant volume CV at 30 Kelvin is 0.81 joules per mole Kelvin, and the divide temperature is 375 Kelvin. And they want us to estimate the specific heat at the temperatures below, which is just 50 Kelvin and 425 Kelvin. Okay, so to solve this one, I'm going to start with part A. So for aluminum, the CV at 50 Kelvin can be approximated by the formula that we just reviewed not too long ago, which is this one. Since the temperature is significantly below that divide temperature that we reviewed recently, and the CV, the value of CV at 30 Kelvin is given to us, which they said was this 0.81 joule per mole Kelvin. So now we know that they want us to compute the, this A, by the way, is just a constant term, a temperature constant. So basically, we need to find this constant so that we can then find the CV for the aluminum at that temperature. So we're just going to rewrite the equation. It should be T cubed. So plugging in the values here. This is our 30 Kelvin cube. We should end up with 3 times 10 to the negative 5 joules per mole Kelvin raised to the 4th. Okay. Rewrite this so that's a little more clear. Okay, so now that we know what that temperature constant is, that A variable, at this point it's just plug and chug. So you have CV, which is equal to AT cubed. You plug in the value that we just found, that 3 times 10 to the negative 5. Multiply that by the 50 Kelvin, cube it, and you should have 3.75 joules per mole Kelvin. So instead of having, so we found it in joules per mole Kelvin, but we need to find this in joules per kilogram Kelvin. This is uppercase CV, so we need to find the capacity at constant volume, which is lowercase CV. So not quite done yet. So to find that, we essentially just take the value that we just found, multiply that by some conversion factors in order to get it into joules per kilogram Kelvin. So this is 3.75 joule per mole Kelvin. You will first multiply this by 1 mole per 26.98 grams. That's the first conversion factor, so the moles will go away and you'll be left with grams. And then the next conversion factor will just be 1,000 grams divided by 1 kilogram. So that would cancel out. So for part A, you should end up with 139 per kilogram Kelvin. So that was part A. For part B, you have to know that so you have to basically understand that chart that we went over earlier in order to understand what's going on. So 425 Kelvin is, if we look at the chart real quick, it doesn't have values, but we can look at it for reference. So the 425 Kelvin that they mentioned is above this divide temperature that they're mentioning. So from there, if you wanted to use, I believe you can use the same method that we just used, but you can also use this approximation, which is the capital CV is equal to R being just the gas constant. So then if we continue to plug that in, it'll just be 3 times 8.311. Joule per mole Kelvin, which is equal to 24.9 joule per mole Kelvin.
But do you have the work problems?
And again, just like in part A, you want to convert the joule mole Kelvin
know what they were?
to joule kilogram Kelvin. So just keep all that since we already know how to do that.
Maybe we can try
You have a CV, lowercase CV of 923 joule per kilogram Kelvin for part B. Okay. So any questions on this one? I think everybody's good on this one. So not too bad. So on this next section, I know number 11 is what people struggle on most, so I'll try to run through this so that we can get to that part. Okay, so the next section that was gone over in your homework was thermal expansion. So essentially, in this section, you learn that how most solid materials expand upon heating and contracting when cooled, and the change of length the temperature for a solid material may be expressed either from this equation or this equation. I notice that in this equation you're using just change in length, and in the bottom you're using change in volume, but basically the same thing. So essentially you have your change in length divided by the initial length multiplied by that alpha L, which is just the Laplace coefficient of thermal expansion, and that is multiplied to the change in temperature, just to find the initial. And same deal with that equation at the bottom, but you're considering the volume of the material versus just the length of the material. And a little bit more on that linear coefficient of thermal expansion is a material property, so it's intrinsic to the material. It's indicative of the extent to which a material expands upon heating and has units of reciprocal or inverse temperature. And so from an atomic perspective, thermal expansion is reflected by an increase in the average distance between atoms. So I guess that's kind of referring to this guy here. So essentially, the stronger the bonds, because we know ceramics, they have covalent or ionic bonds in them. So the bond is very strong. So you're gonna need, I guess, more heat to separate those. Meanwhile, metals and especially polymers, because they don't have as strong of a bond as the covalent or ionic bonds, it doesn't take much to separate those atoms. So in your slides, you can see how the materials compare in terms of thermal expansion. Okay. So for 19.7, the question is stating that there's an aluminum wire that's 10 meters long and it's cooled from 38 degrees Celsius to 1 degree Celsius, and they want to know the change in length, or how much change in length will it experience from that cooling. So let's see. And this one's not too bad. So to figure out the change in length of the aluminum wire, I'm going to hold on a second. Let me make sure I'm getting it right. Ah, yeah. So the equation that we learned up here, I'll just circle it. It's in an ugly circle. So essentially we're using that equation, reorganizing it, so that we can determine delta L, change in length. And in order to solve this, we need to know what the linear coefficient of thermal expansion is, that alpha L. And again, we'll get that value from table 19.1 in the text. So I'll write out the original equation so that way we can see it. And that's just multiplied to delta T. And so again, the question is asking for change in length, so they don't want to know the original length, they just want to know the change. So we need to reorganize this. So that's delta L is equal to L naught multiplied by that coefficient of expansion multiplied by change in temperature. And let's see, oh, so I mean, so this problem's not too bad. I'll let you guys go ahead and plug in the numbers on your end. It's probably going to be different for you guys anyways. The alpha L in this case from table 19.1 was 23.6 times 10 to the negative 6 inverse Celsius. So essentially put that in, we know the original length of the wire was 10 meters and the change in temperature was also given. So this problem's not too difficult to get through. And for this problem specifically, you should have a change in length of negative 9.2 millimeters. So I would ask if you guys have questions, but this one was that easy. But if you do have questions, I'll take them. But if not, I think you guys probably have questions on the next one, because for the people who did attempt it, I noticed there's a lot of people that got like partial points on this one, so something was, I guess, missing, I guess you'd say, conceptually. So let's jump into this one real quick. So number 19.11. So the question reads, when metal is heated, its density decreases, and there are two sources that give rise to decrease in the density. First being thermal expansion of the solid, and the second being formation of vacancies. And I want us to consider a particle at room temp with a density of 8.94 grams per centimeter cubed. So in part A, they want us to determine its density of heating to 1,000 degrees Celsius, when only thermal expansion is considered. And part B wants us to repeat the calculation when the introduction of vacancy is considered, and assume that the energy of vacancy formation is 0.90 electron volts per atom, and that the volume coefficient of thermal expansion alpha V is equal to 3 alpha L. That's a little longer.
No.
Okay, so part A wants us to figure out the density upon heating to 1,000 degrees Celsius, when the thermal expansion is considered. So in this case, we're only considering 1 cubic centimeter of material at room temp, and they gave us the I guess let's see, the volume of copper that they gave us has a mass of, what is here,
That's what I get it, check.
8.94 kilograms, which mass is assumed to remain constant upon heating up to 1,000 degrees Celsius. Knowing this, we first need to compute the volume expansion. So this is going back to this equation here, which is very similar to that top one, but same idea. So change volume divided by the initial volume is equal to coefficient of expansion of that material at that volume multiplied by a change in temperature. And yes, so alpha V is volume coefficient of thermal expansion. And they mentioned that that value is equal to the 3 alpha L. So basically 3 times the coefficient of thermal expansion, alpha L. And so to figure out the alpha L of copper, that's just given in the table again, in table 19.1 in your textbook. But I will go ahead and write it here. That should be 17 times 10 to the negative 6 inverse degrees Celsius. No, I wrote that out. Negative 6 over Celsius. So the volume of the specimen of copper at 1,000 degrees Celsius, if we put that in, so this should be here. So volume is equal to the initial volume added to the change of volume. And that change in volume is equivalent to this guy here that I have in the brackets. The V naught multiplied by that volume of thermal expansion and the change in temperature. And we can just simplify this out a little bit more so that we end up with this here. And then now substituting in that's 3 times alpha L into that's alpha V.
Good.
You end up with
Much.
this multiplied by the change in temperature. And so from here, we would just plug in the values that were given to us. So, well, yeah, I don't like that I did that, that's confusing. Okay, there goes David. Okay, so what we should have here is the 1 centimeter cubed multiplied basically by all this. It's just 1 plus the 3 times the 17 times 10 to the negative 6. And that's multiplied by, that's 1,000 degrees Celsius minus room temperature essentially. Correct. So if you compute that for this, we should have 1.04998 cubic centimeters. And so we need this in terms of density. We have the volume of the copper itself. So we're going to do that into density. You know, density is mass divided by the volume. The mass should be in, yes. So the mass is just 8.94 divided by this value that we just found here. And you know, it's just mass divided by volume. We're going to just write this out. 8.514 grams per centimeter cubed. So for part B, they want us to compute the density at 1,000 degrees Celsius, take into consideration the creation of vacancies, which will further lower the density. And this should ring a bell because we learned about vacancies and whatnot way earlier this year. So I'll go ahead and write that out. So, to determine, yes, the number of vacancies. Yeah, so in order to determine the number of vacancies, we need to first figure out how many copper atoms per cubic centimeter, which is this N subscript C U, which is just copper. What that volume is at 1,000 degrees Celsius, which is what we will, how we'll figure out using this equation. So this N subscript A here is just, I believe, Avogadro number, which is just 6.022 times 10 to the 23 atoms per mole. We divide that by the density that we found in part A, which is the 8.514. And multiply by that, divide that by the atomic weight of copper, which is 63.55. And you should end up with 8.07 times 10 to the 22 atoms per cubic centimeter. And so now to figure out the total number of vacancies, since we now know the number of copper atoms within that basically cubic centimeter, we'll calculate that by using this equation here, which we also learned about way earlier this year. And so here is where that's 0.9 or 0.9 electron volts per atom comes in, so that is just your QV. So QV is the so again, this part is just kind of just plug and chug in. So I'll just get to the end for this one. I'll let you guys do the calculation on your own. In the interest of time. So you should end up with number of vacancies. It has 2 points. 212 times 10 to the positive 19. Vacancies per cubic centimeter. I have like more steps to go for this one. Okay, so now that we know the number of copper atoms in that cubic centimeter and we know the number of vacancies, we now have to determine the number of vacancies per unit cell. So we'll see this one here. So we essentially calculate the unit cell volume, which is just this equation here. Okay, so copper is a FCC metal. So to figure out the number of atoms per unit cell, let's just write that here, and it's just 4 atoms per unit cell. And we solved for everything else already, or we know everything else already, so I'll cut to the chase with this problem. And that should equal 4.958 times 10 to the negative 23 cubic centimeters per unit cell. So a lot of parts as well. So I'll say 1, 2, 3. So I can say part 4 of this problem is now we're going to figure out the number of vacancies per unit cell, which is what they call lowercase v, which is the number of vacancies multiplied by the volume of the unit cell. And you know those values already. Vacancies per unit cell. And so what this means is that instead of there being 4 atoms per unit cell, there are only 4 atoms minus that 0.001097, which is 3.99 atoms per unit cell. So finally, the density can be computed using this equation here. So I'm going to rewrite this. So nothing that is mentioned. So there's theoretically 4 atoms per unit cell, but as we just calculated, the vacancies per unit cell, that's 4 minus 0.0019 or 0.017. That gives us about 3.99. Say 8 here. So this n actually has to go here. We know the other variables, the 1 per unit cell, atomic weight, and Avogadro's number. So to solve for that, or plug those values in and solve, I should say, the density of the copper should be 8.512 grams per cubic centimeter. So we did all that, and the theoretical density for copper, and I guess you can say the actual density for copper at this temperature is like so small that you guess you can say it's insignificant, but there you go. So that was a lot, but I know number 11 was one that you guys had questions about. Leave that here, give you guys a second to write it down. So any questions on this one? Okay. So, real quickly, so that we don't run out of time, we want to go ahead and review final exam stuff. If we have time at the end, we can still keep going over this stuff, but we could always leave this as well for next time. I think we have like 3 or 4 questions left. There's still a couple of sections left over. I know number 11 was the hardest one out of the bunch, so it was the second. We're gonna pull up the old slides and stuff, and we can answer some questions that you guys might have for final exam.